Okay, going to go ahead and get started. So, hello everyone, and welcome back to the Beyond Backup webinar series. My name is Khalif Woodard, Senior Marketing Manager here at Intelligent Generation, and I will be your host today. Winning a storage deal and signing a contract is a huge win, but navigating utility interconnection, managing engineering constraints, and coordinating post-close operations is really where projects are brought to life. Today, what we're going to do is peel back the layers on utility engineering and laying out the exact roadmap for taking a project from signed contract all the way to commercial operation. Before I hand things over, a few quick housekeeping reminders. Please use the Q&A box at the bottom of your screen to submit your questions throughout the presentation. We're saving all the questions for the end. We have a dedicated time at the tail end to answer all of them. Also, if you would like a copy of today's video recording, the slide deck, or the session notes, please reach out to me directly after the call, and I will gladly send those to you. To walk us through today's topic, I'm joined by two outstanding speakers. First, from Intelligent Generation, we have our Director of Business Development, Eric Gronwick. And joining us as our featured guest speaker is Nathaniel Hurst, or Nate Hurst, professional engineer and principal at F.utility PLLC, an engineering firm specializing in complex utility coordination, renewable energy, and medium voltage design. Without further ado, Eric, I'll hand the floor over to you to get us started.
Thanks a lot, Khalif. And everyone, thank you for joining us today. Today is kind of a fun opportunity for me. It was about a year ago that I was, as a channel partner, attending Intelligent Generation's first Power Partner webinar. And at the time, obviously, I loved the content, but I was equally as impressed with and appreciated the fact that these are exclusively for our power partners. Like, this is not open to the public. We could probably get a lot more people to join our webinars if we were to open this up, but really, we view our partnership and take it very seriously. We know that if we help set our partners up for success through education and sharing ideas and learning together, that's how we're going to be successful as well. So, and the other fun part, of course, is that I get to co-host today's webinar with my friend Nate Hurst, who we used to work with together at a EPC developer in the past. And when we separated ways, I thought, yeah, we'll maintain a friendship, but not so sure we'll work professionally together again. And here we are, Nate. So this is pretty cool. I am going to allow Nate to introduce himself because if you get to know Nate, and hopefully you all will, he is probably a runner-up for the world's most interesting man. He's got a lot of aspects to him. So I'll let Nate introduce himself real quick.
Sure. Just to give a short summary, my name is Nate Hurst. I've been in the engineering industry for 12, 13 years now. I've been a PE for about 7 of those years. The first decade of my career, I worked heavily with ComEd on an engineering basis, did a lot of the large buildings in Chicago, kind of during that 2015 to 2020 construction boom in the city, developed a lot of expertise with service connections, new feeder deployments, distribution automation, things like that inside the city. Took that experience and leveraged it for the renewable energy world effectively. Working at the service entrance, getting renewable energies interconnected. It's not incredibly different than those new business projects. Since then, I've put maybe 35 to 40 megawatts of solar under my belt, ramping up to close to 10 megawatts at best now. And, really eager to see some of these new technologies get deployed on the grid. ComEd was the first to really get a smart grid developed. Locally, Illinois Tech was the first to deploy a strong microgrid, and those are types of technologies that are coming commercially available for everybody right now. So I'm really excited about that. In my free time, I also run Disc Golf Chicago, which is a local charity that focuses on bringing programming to youth centers like the Forest Preserve Park District and Chicago Public School Systems. We've got a couple after school teams and things like that, the local grade schools. So, if you're not catching me at engineering, you might be catching me out there playing disc golf or playing my saxophone around the city somewhere. But yeah, I'm eager to talk about utility interconnections and try and scare everybody a little bit about the level of effort and level of risk. So we're taking it seriously and planning accurately. But most importantly, I'm excited to be here. Throughout the 15 years of my career, the amount of things that I've seen wrong with the grid that can be solved with batteries makes me really motivated to, invest in this technology. So I'm excited to be here today.
Awesome. Perfect, Nate. Khalif, would you bring us to the next slide? Cool. All right. So the topic for today is post-closing activities. And as you can see from the graphic, and this is not a new world for all of you that are on the call with us today, there's a lot of ground to cover. We're not crazy enough to think that we can cover all of this in today's webinar, and so we're not going to even try. We are going to focus on utility interconnection and best implementation. And those topics are, I think, the two topics that we bring the most value to. We have a lot of experience with both, obviously. Just interacting with our power partners, these are the topics that, people are coming to us with questions and asking for information, things like that. So we're going to spend our time focusing on those two aspects today, specifically. So, and I think from there, we will let Nate take over and talk about interconnection.
Cool. Okay, so the format of the presentation, I don't want to beat everybody over the head with the information bat too hard today. A lot of things that are specific figures about interconnection are tough to be memorable, and they're easy to look up and easy to review. So what I wanted to do was kind of build a mantra here for the right way to go from a set target from the contract and from contract signing and sort of chip at it and mold it and get it as close to the original target with a pragmatic and feasible interconnection design. And from that interconnection design, you'll be laying the groundwork for all of your detailed design engineering. And there's some things that just aren't as obvious when you're looking at it at the beginning, when you're looking at interconnection design or when you're looking at signing with the customer, that begin to rear their head as you go through the process. And generally with these types of projects, if you're going to have to make a change eventually, if it's inevitable, it's really great to do that as early as you can, right? And get as much lead time on the changes, get as much heads up on what you need to do differently, and avoid sinking cost into things that aren't eventually going to be successful. So this is the carousel. You could take this model and you could map it over a lot of problem solving, but we start at the top left and we set our target. Generally, that comes from the customer's apparent need, right? We see the utility bill, we see the customer size, maybe there's existing solar, and we say, okay, this is about the size of the system. Financially, this is the size of the system that would benefit this customer the most. And we set that as kind of our golden goalpost of, in a perfect world, this would be our best solution. And from there, we go to the site, we collect our information, we find all the records, collect information from the utility, vendors, everybody, and start arranging the puzzle pieces and seeing what won't fit with our target, right? And we move down to assess constraints. We've got all of our information, we've got our target, what constraints are going to stop us from getting to that target, and what can we do about it? And once we have that groundwork laid, we develop our strategy moving forward. And often that strategy includes revisiting the target and adjusting it. And what you'll find sometimes is that those small adjustments are far more tolerable than trying to chase the dragon and get up to that ideal situation. There's a loss of efficacy, diminishing returns, however you'd want to describe it, some cost fallacy there. So next slide, please. Kind of digging into set target. How do we initiate our goals here? This is a loose priority order, but obviously fulfilling contract requirements, right? Pretty much number one. Contract requirements are typically fairly ironclad and or backed up by some sort of damages if you miss them, right? So it's really important to at least treat that with the magnitude of that cost basis. You know, at the end of the day, we're all here to complete these contracts and benefit from them mutually. So that's kind of the golden target. And if it needs to be adjusted, it needs to be adjusted, but that's what guides everything. Supporting those figures is what we're all here for, commerce, right? Everybody involved in the deal wants to make something from that deal, whether it's a performance benefit or a cash benefit, any kind of investment that they're getting from it. You know, nobody wants to work on these for free, so to speak. So, you know, protecting your investment, that's another high priority. And then this is where we get a little bit more subjective. Deliver a product with high quality. In my opinion, the rule of engineering is you never really want to chase perfect quality. You want to chase good enough, and that's typically your best solution. High quality is important because we want them to perform, and we don't want them to have interruptions, right? Poor quality is more than just possibly ruining a customer relationship. Poor quality could destroy your return on investment. Poor quality could invalidate your contract requirements. High quality and a plan to maintain that high quality is paramount. It's QA, QC, O&M, smart partnering, smart forecasting. And that drags us to cover your liabilities. Now, this sort of seems the most optional, but at the end of the day, it backs up the other three in the tower here. Is you do not want to leave yourself with liabilities that could defeat the whole process. Kind of the most famous example that I use lately is having a pole installed with a recloser on top get knocked down in the wind. If you don't have telemetry to measure that wind, if you didn't have some sort of study that says that pole's got to stand up, you know, the insurance company has no engineering data to know if it would have been knocked down on its own or not. And those type processing a claim on your big fancy $200,000 recloser computer gets a lot more difficult then. You know, covering your liabilities is more than just engineering and permitting. It's basically everything that your insurance might need, and then maybe a little bit more that they're not, you know, explicitly requiring. And I guess the last piece of cover your liabilities is don't leave yourself in a position where it's impossible to meet your targets. So, you give me the next slide, please. So moving around the carousel as this presentation is formatted. Really, really important to do first is aggregate your records. So aggregating your records lets you know how much of the site, how much of the facility is already engineered out, how much is already established, certified, etc. This is something that really, really, really becomes important behind the meter as you get to larger projects. There's all sorts of things that occur later on. Where you have to figure in the characteristics of your own battery or solar renewable system and the customer's existing facility. If you don't have an established record of that existing facility, that's when you have to begin investigating and rebuilding that data set, something you might not be prepared or qualified to do. Real estate investigation kind of falls in the same lane, except with the real estate agreements. We didn't start digitizing real estate agreements until computers were common. So there are a lot of real estate agreements that are not accessible by your common GIS platforms that you send a real estate lawyer out and they find, oh, guess what? There's an easement here written into the lease by hand in 1895 that's still technically valid because it didn't have an expiration on it. All sorts of little things like that you might have to figure out. Utility information requests, similarly, it's almost as if you're pulling record data from the utility. As a general rule, any and everything you can figure out about your utility's characteristic nearby can be valuable for you during site design. Of course, the most significant is the power configuration compatible with my battery? Is it compatible with my system? Most of us know about capacity maps and things like that. There's a bunch of tools available to us that will let you predict your success odds. You know, that can also be just a customer's existing utility information. You know, one of the most common pieces of data input we use as developers is the utility bill. And there's more available than that, the utility bill. Sometimes there's service agreements written into place. Sometimes the customer has existing contingent plans with the utility, and sometimes it's obsolete. Historic metering data. Historic metering data tends to figure into the same thing as utility information request. Your utility bills are metering data, but it also applies to larger systems, commercial and industrial systems that have sub-metering to figure out where their load flow goes, figure out where their power goes inside the plant. Having a sophisticated understanding of those complex systems can become really important to know where to connect and how to connect. And just the general size and schedule that your customer is using their electricity. Historic interconnection agreements. This is kind of a no-brainer. If you're expanding on existing solar, have all the data about the existing solar ready to go. ComEd's going to tie those bureaucratic records together. So you're going to want to be privy to both of them, especially if you weren't the original builder for that solar. Equipment manuals. A lot of times we go into projects and we kind of already have our eyes on the prize for what kind of equipment we want. Getting as much data from those manufacturers as possible can help you iron out incongruencies that you didn't expect. As you're going through equipment, sometimes a particular inverter doesn't have a communications protocol you need. Sometimes a particular battery needs a special function from the inverter that you didn't know you need. Proofing those out in advance avoids having to swap them in the future and causing any kind of modifications to your design. And then lastly, site operating diagrams. And this, again, with heavier commercial and industrial, not every site's as simple as just flipping off the main breaker and everything goes and de-energizes, right? Sometimes you flip off the main breaker and a generator automatically turns on. Sometimes you switch off a main breaker and the second utility power line engages. Site operating diagrams are really important. Also to know that you're not interrupting the operations of the site while you do your work. If you install those kinds of batteries next to a generator, you could be interrupting the generator's controller's, relay and control profile. So that's not something that you want to do. You want to be, well informed of those things. Next slide, please. Okay, access constraints, capacity. This is a big one. This is a very, very different situation with batteries than from solar. So Cleve included this graphic here, which is a bit eclectic, but it really does get the point across. With solar, we benefit from the fact that it only generates. So your utility can both push or pull. Your solar can generate. Your site demand can only pull. And in that three-way junction, your solar is either always going to drain into your customer or drain into the grid. Because of that situation, all three legs of that three-way junction could be the same size. Now, when you introduce a battery to that whole intersection, you're introducing another device that can both deliver and absorb energy. In a situation where your facility and your battery are both working 100% and they're both sized at the same level, now your facility is consuming twice as much power unless you stop that from happening. Similarly, depending on the way your conductors are built, where you're interconnected, your battery's charging at full speed, your solar's contributing at full speed, your site's using a full amount of power, and you're connected to the utility. Depending on if those junctions overlap, you might create a spot where you have twice as much power flowing through the conductors than you expected. This is really, really important with batteries when you connect them to determine that the existing facilities are not going to be overloaded. It's also really important for your service drop to make sure that the utility itself is not going to be overloaded, and understanding what level of control and protection you have to do in order to stop that from happening. In certain situations, that might be as simple as adding another breaker that clamps everything down in and out of the utility. And if you want it to be more sophisticated than that, that breaker might be something with some level of intelligent control. The NEC in UL, IEEE, they're all now recognizing power control systems as a legitimate means and method for controlling current. Many batteries have these functions built into them, but as the site gets more and more complicated, as there's more and more variables on the customer side, those begin to be a system you have to design from a top level master view topology. And that's where batteries can get a lot more complicated than solar because of that in-out function that sort of changes the math throughout the day and makes it a lot less predictable unless you provide a very clean and precise operating characteristic for the battery. Another thing that I want to point out here on this slide, this is one of the many boogeymen of these projects, fault tolerance. Inverters, batteries, solar, they store a good amount of charge. And every electrical system that you work on will have a interruption capability. It's very important that the extra devices you put onto a system don't exceed that interruption capability fault tolerance, or you'll be upgrading everything. Can you give me the next slide, please? Thank you. It's like we might have lost the presentation.
Did we lose Khalif?
Yep. Sorry about that.
Okay.
Great. Okay, so continuing on with the access constraints, what's going to limit us? Size, space, and setback. So this is something that the solar industry has been working to create a great golden rule set for size, space, and setback. We've got a pretty regular size of module, half module, bifacial modules. They're pretty commonly sized, pretty ubiquitous. The space required to install ground mounts and roof mounts is generally accepted, and the setbacks from property lines and buildings. We have all sorts of industry rules to support that. When it comes to batteries, municipalities are just getting on the bandwagon now. Certain municipalities may not even recognize different battery chemistries. Certain municipalities may have requirements that are far greater than the overreigning jurisdictions that we would otherwise be paying attention to. And as new technology comes out, we have new ways of managing those sizes, setbacks. You know, for the longest time, the Tesla Megapack was the golden standard. The lithium chemistry has competitors now that are fireproof. But those fireproof competitors require a lot more physical space, right? There becomes a push-pull. We can get a megawatt of battery power from a lot of different technologies and a lot of different shapes and sizes, and something is going to be ideal for whichever site we're working in. I think the most famous example is when you're working on sites that have high combustibility risk, volatile chemicals, volatile dust, fine dust, things like that. Devices that are not at risk of fire become a lot more attractive despite the additional requirements for size and space. Similar, certain devices that can be built up vertically on racks may present a huge efficiency for small sites that allow vertical construction. You know, something in the city, we see that all the time residentially. These small parcels support a 2 or 3 flat apartment building much better than a single family home. And that same thing works for electrical capacity and architecture. As you're installing these systems, though, you have to continue to pay attention to the existing equipment. And we've loosely touched on a few factors of the existing equipment that can haunt us. But like many things, you break it, you buy it, is our biggest demon here. Obsolescence, right? Electrical equipment changes fast, and something that's still working, that's 30 years old, may not have any repair parts available for it. If you break a single piece of that, you may become liable for replacing the entire system or structure. And with some of these large C&I customers, it doesn't just stop at replacing the equipment. You become liable for their downtime as well, and downtime can be way more expensive than any of the equipment ever was. When you modify a lot of these existing gears, the vendors, the original manufacturers of those gears, will have stipulations that you're required to follow to maintain the warranty. There's a large cost basis that the eventual owner and customer will lose if they lose their warranty on those gears. And similarly, if you modify it, you might have to recertify it and relist it with UL. And it requires a third-party testing laboratory to come out and visit. So understanding the extents of that and what you'll need to do becomes a very rigid but not unbreakable constraint that, you know, when we're going back and assessing constraints later, we'll revisit. And the last piece of existing equipment, communications. We really have to be strong about communications. IP services are really, really important for operating these batteries. High quality, low ping, readily available internet means that every signal we need to send the battery to make it work correctly is going to get to the battery on time. And when batteries are better than the competitors because of the speed of deployment. That is an integral part of our engineering design. Quickly, load flow analysis. I touched on this a bit earlier. Your new 4-way junction has a lot more complex load flow than the old solar plus load plus grid. It's important to tag in somebody who can review that with a fine-tooth comb and plan for any exceptions that might be occurring. Next slide, please. And I'm going to skirt through these next couple a little faster because the slides get a little more verbose. I want to make sure I leave Eric enough time. But, you know, this is the kind of topic I could talk about it for days. So control. This is probably my most important slide as far as what to be thinking about for these battery systems is what are they actually going to do? Solar, you just turn it on and let it run. Batteries, you have to tell them what to do. You have to give them a plan, a schedule, a scheme, program them somehow. And as you make these big battery systems, there's a lot of control systems you have to have in place as well. So first, determining behind the meter community supply. You know, that's roughly the same equation as our solar. Distribution automation. Again, you're much more likely to graduate into a situation where ComEd asks you to install a recloser when you've got a battery down. Distribution automation is challenging, comes with its own set of ComEd requirements. They need radio coverage, radio signal coverage to operate their recloser. And you also have to have your own recloser that has to be coded to meet the standards that they require. It becomes a large engineering exercise. Data acquisition systems, not just for Illinois shines, it turns out. You know, a lot of the times we're using our DAS, it's to grab our revenue grade metering data and submit that to some benefactor. But the DAS system also gives you a lot more information that could be useful for warranty claims, liability proofing, and general performance monitoring. Super, super critical to have data acquisition systems to make sure that you are checking your battery's performance for parity against what other parties are telling you your battery is performing at. And then the big one we're here today, operational performance. Making the battery work in a way that actually renders a benefit. And now this one is really challenging, but is a great way to tee up intelligent generation's role. You know, in certain environments, in certain settings, batteries can run autonomously by giving them a script. With the type of systems that we're trying to build, these systems are deployed directly by a market participant. And these systems are also deployed on a fairly esoteric schedule and implementation. It is very important from engineering, from hardware, to provide a system that allows your operator comprehensive control of the battery's performance. This could mean making sure that you have multiple points of communication for the battery. It could mean configuring your network with your data acquisition partner to provide command forwarding. It can mean a lot of things at a system implementation level, but everybody who needs to provide control to this battery needs to have access to it. Protection scheme and telemetry requirements fold into each other, but ultimately, the more sophisticated we make our system, the more telemetry we need to monitor what's happening in our system, and the more sophisticated our protection scheme has to become. And those last 5 bullet points here, the main 5, those all interact heavily. Your operational performance system is going to keep your system running when things are normal. Your protection scheme is going to make your protective devices work when things aren't normal. Telemetry is going to tell your system if it's normal or if it isn't normal. And your data acquisition system is going to let us see that without being at the site, measuring it with our own meters. And if there's an emergency, the distribution automation will kick it. Next slide, please. So what's our strategy? Start with absolute constraints. What can't we avoid? What has to happen? What are we beholden to by what we've signed? What is an ultimatum? So those are things we can't change about the system. We apply our rigid constraints. What can we change, but it's really unfavorable to change? These are the kinds of small nudges that unlock more pathways in the future. The classic example of this is replacing the customer switchgear. In a theoretical example, if we downsize 10%, we don't have to replace anything. If we go with the promised size, we have to replace everything. The replacements are going to cost far more than 10% of our cost basis for profit. And then you start to think, okay, now there's a seesaw. We give it to the finance wizards that are part of every team and say, hey, help me model this out. What's going to be most advantageous for me and my customer? So we optimize and revise, get around the carousel and go back to setting the target. So I got a few more slides here now that will just kind of depict some more specific warnings and some more, threshold requirements to get people thinking about what does this design mantra mean for my system that I'm planning? Which boxes do I fall into? Where do I need to be careful? Next slide, please, Cleve. So to outline, interconnection is regulated by Illinois Commerce Commission, right? The state law makes the rules. They work closely with the utility to make those rules, but they are ultimately the one holding the utility accountable for following their rules. So while those do seem challenging to fulfill, ultimately those rules are to protect us, the consumer and the owner, from the utility. On top of that, each electrical distribution company has their own compliance code and standard. And that's something that we have to see as superseding the requirements from the state, so long as they are cooperative with requirements from the state. And when we talk about batteries, almost every battery project will be a level 2 or level 4 interconnection. Level 1s are very small. Level 3s don't export. We're always going to be exporting our batteries for frequency regulation if possible. Level 2 applications are very rare. Very, very, very rare. What a level 2 application ultimately represents is you've decided to do a project that has day 0 readiness from the utility. They checked, they said, you're right, that will work. Good luck, go ahead. That's great. I can count on one hand on the amount of large projects I've gotten through on a level 2 interconnection, and mostly just, 250 kilowatts of solar, stuff like that. It's very, very challenging, even if you do everything perfectly right, to have a site that's eligible for level 2 interconnection. So level 4 applications represent all of their best projects. They typically exceed the 6-month timeline, 25 days setup time, 6 months execution time. And it's sort of just the beginning of the whole dance there. Can I have the next slide, please? So here's your level 2 eligibility. And I want to bring this one up because I see this as a bit of a lure. These sizes, as presented by the ICC, are the absolute maximums that something can be a level 2. And they do line up pretty well to how the utility sizes their feeders. I will say, in practice, the thresholds very frequently are much, much tighter than this because of some other ancillary condition on the power line that violates one of the sub rules that shoves you from level 2 to level 4, typically called acceptance studies or interconnection studies. Can I go to the next slide, please? So what are some important threshold requirements outside of what the ICC requires? So speaking from ComEd's world, level 2 applications over 1 megawatt, level 4 applications have a variety of design factors that require a PE stamp just to apply for interconnection. This is really important for things like sizing the transformer, sizing wire, overcurrent protection devices, and most importantly, relay and control protection schemes, which are fairly niche, fairly esoteric. It's very important to get an engineer tagged in that can stamp your drawing. They don't necessarily need to be an engineer record that will be your electrical or civil engineer all the way to the end, but they need to be somebody that can create a package that can bring in those engineer record partners in the future. Any project greater than 1 megawatt, less than 5 megawatts, right? And a reminder, this is all right out of the ComEd interconnection standards packet. You can go ahead and have a SCADA system with a 5-minute reporting interval, right? What this means is effectively your data acquisition system has to also report to ComEd on a 5-minute schedule. If you go over 5 megawatts now, which once again, we get into the territory of pretty rare, now you have to have your own SCADA reporting system that reports at a 30-second interval, right? And what that means is that your telecom system to the site is going to level up pretty significantly there. Finally, any project with an energy storage system is going to be requested to fulfill a grid charging and export characteristics report. This report is probably the most important thing to mention on this call, because this report is not detailed well by any ComEd standard, but your friends here at Intelligent Generation can provide a lot of help on that report. And I would say it is imperative to have their blessing on what information you put in that report, because that report, once you submit it, is law for how your battery will perform. And you must not make a claim on your battery's performance that we cannot fulfill. That is the most important thing, is not only will Intelligent Generation make sure that you are doing the ideal characteristic report, they will also make sure that you are not setting yourself up for an impossibility by boxing yourself into a requirement that you can't fulfill. So if you take anything away, know that that's coming during your interconnection application, and bring it to Eric, Khalif, and Dave when you get it after your first pass. Looks like I think I got one more slide here, or two more quick slides for me, and then I'll hand it back to Eric. Sorry, Eric, I know I'm about 8 minutes long here. Subsequent specialized studies with the level 4 interconnection require schedule extensions. So when stuff gets really weird, ComEd has a whole nother list of studies that they may need to perform. These are pretty typical when it comes to level 4. And if you've ever had a project that was stuck at ComEd for longer than 6 months, they're probably looking at the substation or some other customer on your site, or some other weird, unique condition that they have that they need to put actual engineers on their side to work on. Once the interconnection agreements are finalized, that is when Ameren or ComEd will finally start their detailed engineering design. This is really critical too, because once they begin their design, it's a whole nother wave of them pulling the veil off and potentially, putting you in a bad position. We know that utility projects are measured in years. We know that everybody enters the queue and exits the queue in a first in, first out basis. And we know that material modifications to your projects will cause you to restart your interconnection application. It's very important that you have a firm and comprehensive understanding before applying and before finalizing your design. Otherwise, ComEd's going to kick you back to day one and ask you to resubmit your application fee and everything that comes along with that. So I wanted to rush through the last couple to make sure I preserve the time, but I'm available for questions. My schedule these days is pretty busy, but F.utility is growing rapidly. We're onboarding more engineers. We've got 4 people, an architect, a QA/QC manager from overseas who's got some European experience as well as a dedicated design drafter. So happy to help out with small stuff, and let me know. Thanks again for having me, and I'm looking forward to hearing your half of the presentation, Eric.
Thanks a lot, Nate. Very thorough. And as someone that's been in sales and business development my entire career, I love knowing technical things, because it helps me, after sale is made, make sure that it can get built. So great stuff today. We appreciate it. I'm going to go back to slide 3 for a minute, just because I didn't dwell on this initially because I wanted to get us rolling. But this is something that you're probably all familiar with, but there are a few tweaks to it. I think the one thing I want to point out here is that, that I'm going to be talking about BESS implementation. And as you can see, it's kind of scattered throughout pre-construction and construction phases. We will start BESS implementation at the same time that our channel partners, power partners, will be working on procuring and planning and engineering and permitting. Once interconnection is done, we also want to start our process, because some of the things, and I'll get into more detail in a minute here, but some of the things require time, and we want to make sure that when the battery gets PTO, we're ready to do our part. The other thing I want to point out here too is that testing and commissioning, as you can see, is in there 3 times. It's kind of obnoxious, but it is intentional, just to remind all of you that after PTO from the utility, there's going to be testing and commissioning from the battery manufacturer, and then after that, testing and commissioning from Intelligent Generation. Khalif, will you go to slide 17? 16, sorry. Perfect. All right, so I'm going to be talking, this is what I'm going to be talking about. Again, we start our process in pre-construction. We finish our process in the construction phase. And then we are also participating in testing and commissioning. Again, I would allow 4 to 8 weeks from when PTO is issued from the utility before the battery can start operating accurately and officially. Okay, so as you can see here, we start our PJM registration in pre-construction. That takes several months. I would liken it to an interconnection process. There's going to be back and forth between ourselves and PJM. There's also going to be a little bit of back and forth and involvement with ComEd in that process as well. I think we all know how cumbersome that process can be with, responses, and then it takes a while for another response to get acknowledged and reviewed and responded to. It's just a lot of back and forth. We don't want to be in a position where the battery is not ready to operate once PTO happens, because, every month it could be tens of thousands of dollars of lost savings and revenue. And that adds up very quickly. And also, I think the thing to keep in mind too is that increasingly our queue is growing. So it's not just, one battery that we're registering at a time. It's multiple, many, and that number is growing. So we also have to kind of keep in mind that we do have a queue that's pre-existing, when all of you bring us a project that's, post-closing and needs to be started. All right, next slide, Cleve. Here's some more detail about that beginning process, that PJM registration. These are the documents that are going to be required, things that already are existing. Just wanted to make all of you aware that, we will need the single line diagram, the signed interconnection agreement, a recent utility bill, and then obviously, the final determining factor of size, manufacturer, and model of the BESS. And that is when, and we're not going to start that process until we have all those things. And we also are not going to start that process until there's a setup agreement in place and that setup fee payment is made. And they all kind of line up, because what we're asking for is for that setup agreement to be signed, that fee to be paid at the first milestone after notice to proceed. Notice to proceed can mean many things to many people. To us, it means that there's a signed interconnection application agreement, and it also means that the PO has been submitted for the battery. At that point, we feel like, that's a commitment to a specific battery manufacturer. So then therefore we can start working on our part knowing that. And it's also an indication that this project is more than likely going to get built. And therefore that's the time that we want to get started on our things as well. Next slide, please. Okay, so some other things to keep in mind with this PJM registration. It does take several months. We do want to start at notice to proceed. We want to complete any programming, pretty early on. A lot of the things won't be completed until the construction phase, but we do want to start it early. There's going to be, IG testing and commissioning. They're going to be happening after construction during the testing and commissioning phase. After that, of course, then we still have some PJM market onboarding that has to occur. And then at that point, we can actually start commercial operations. And again, not to be redundant, but we want to drive this point home, is that can be, as fast as 2 weeks. I wouldn't count on that. Could be as long as 8 weeks. And I think be prepared for that. Something that I think is also important to mention right now is that, frequency regulation can start any month of the year. So if a project gets PTO in October and the battery is fully operational December 1st, we can start frequency regulation activities December 1st. if we're talking about on-bill savings, where we are trying to reduce our customers' capacity and transmission charges, that season that determines that starts June 1st and it ends September 30th. So if the plan is to have the battery operational June 1st and PTO doesn't happen until May 1st, there's a likelihood that the battery is not going to be available June 1st, and it could miss out on one or two or several of the 5 peak hours during PJM's calculations and the utilities calculations as well. So we have to kind of keep that in mind and kind of back things up a little bit. Next slide, please. All right, during testing and commissioning, these are some of the things that we're doing. Again, I think what we're trying to do here is just share some insights, lift the veil a little bit on kind of what the activities are that we're going to do. And I don't need to read all these to you, just to kind of give you an example of the things that we're doing behind the scenes, that if you haven't done a battery project with us yet, these are the things that you can expect and anticipate. And Khalif, is that the last slide? I think so.
Yes.
Okay, perfect.
Okay, right. So are you wrapped up?
I'm wrapped up. Thank you, everybody.
Thank you. All right. Thanks, Eric, and thanks, Nate, for breaking down what's usually I would say a very complex engineering and operational maze into a clear step-by-step process. So we have about 10 minutes left. I'm going to open up the floor for Q&A. I didn't see any questions dropped into the chat box, so I'll go ahead and ask a few questions myself. Nate, you had mentioned that the level 2 application can easily get escalated to level 4 during EDC screening. What would you say is the most common trigger that pushes a commercial project out of level 2 into that 205+ day level 4 review process?
Typically, with the batteries, we don't operate them all day at the same speed, right? So in order to be in level 2, your battery has to be, no matter what it's doing, it has to fit, on this customer system, on utility system, utilities control mechanisms, everything just has to be day 0 ready. When you look at the way intelligent generation operates these batteries, they do so with a lot of intelligence, right? It's in the name. There's a very smart way of deploying these batteries at opportune times. And those opportune times have a relationship with the times where the grid is doing different things. And that's what makes them opportune. When a battery will fit on the grid when we need it to, but not always, ComEd's got to do some analysis and make sure that we're correct in that assertion. And I would say that's pretty much the number one reason it goes to level 4. If you want to think about it in bureaucratic terms, is if ComEd's got to pay their own engineers to spend time doing that work, then that's going to be a level 4 interconnection.
Okay, thank you. I appreciate that. Eric has a question. So how much time should we plan for the interconnection process, including interconnection application preparation, ComEd or whatever utilities full review, and the ComEd steady results along with approval?
From day 0 to we're approved and we're talking about pre-mobilization activities, it can vary wildly, but I don't think anybody should count on it taking less than 9 months. I think you can get, when you're really, really lucky, you can get through that process in 4 months, start to finish, as the absolute fastest, I think. That's very rare. I've seen projects take upwards of 18 months for that procedure. So, I think it's the kind of thing where better safe than sorry. And you should, as soon as you feel confident that you have a comprehensive path forward, you should start moving on the interconnection application. The worst thing that can happen is that you find out more information. So it is a good process to start as early as possible.
Good, thank you.
Awesome.
We got a request from Mark. Eric, could you elaborate on the need for developers to push for net metering designation to happen quickly with ComEd billing after PTO? We are finding that ComEd interconnection application signing PTO with NM is not enough for ComEd billing to accept it. Developers cannot count on this to happen by itself.
Yes, actually, Mark and I have had conversations about this. So, Mark, I appreciate you asking me a question that I'm familiar with. Back to my solar developer days, I knew that, PTO takes a month. I knew that net metering wouldn't necessarily show up on bills until the third or fourth billing cycle. So I knew that those things were delayed. What I didn't know about the best side of things is that if we want to start battery operations, let's say 4 weeks after PTO, let's say the manufacturer testing commissioning went fast in 2 weeks, our testing and commissioning goes fast in 2 weeks. So we're ready to go 30 days after utility PTO has been issued. And no one has been pushing on the utility to get net metering in place, then that could delay operating the battery and generating savings and generating revenue. So it's really important, EPCs and developers, that during the construction process, even though you don't have PTO yet, continue to communicate with the utility about net metering. It can be done. They might tell you that it can't be done until PTO has been issued, but things can be done to make sure that everything is in place so that when PTO is issued, net metering is available right away.
Thank you, Eric. We actually have a question from Alan. So how are best projects rejected from interconnection, and what costs should we expect to accrue prior to the interconnection approval?
I think that the big thing to remember is that the battery is its own load, right? And when you apply for a big battery, ComEd treats that almost like you're adding new large load. So I think that's the most common way they get thrown out, is that you're asking for too much load and ComEd can't deliver it. A lot of times when ComEd can't deliver load, they'll offer a plan to expand a facility in order to offer that enhanced load. And sometimes they've already tried that for somebody else and found a third-party external reason why they can't. The most famous example would be that the substation is physically at its occupational maximum, that in order to make it bigger, they would have to acquire new real estate, which due to the constraints of the site just isn't feasible. Sometimes that happens. Sometimes it's a matter of the power line. So, there's investigation you can do with that utility information request. You can try and get ahead of that. You can do things that limit your site so that you don't have coincidental load of the building and the battery. And I'd say if you're really trying to be proactive, that's the big thing to look at, is making sure that you don't have coincidental load between your battery charging and your building utilizing full power. It's something that IG plans to avoid, but sometimes you have to spell it out specifically for ComEd. And during that process, costs you can expect, level 4 application costs can go all the way up to $2,000 plus another $2 per megawatt. But then as you get through the additional levels of studies that ComEd has to do, there are additional funding requests that say, hey, if we have to do this additional 45-day study for you on your behalf, we need to pay our engineers. Here's a cost associated with that. And they'll give you a chance to reject that, but rejecting it means withdrawing your application. So the most I've ever spent on a application was $20,000. I've heard horror stories of people spending quite a bit more for 10, 20 megawatt systems. But $10,000 to $20,000 for a very, very, very large level 4 system would be a conservative estimate. Outside of the rest of your due diligence activities, of course, that's just with your commerce relationship with ComEd.
Thank you. I got one more question. So for projects over 1 megawatt that trigger the distribution automation and SCADA reporting requirements, how would F.utility and IG collaborate to ensure those hardware telemetry specs are baked in before engineering designs are finalized? What does that look like?
Well, so ComEd has a standardized set of requirements for interconnection that give you a very precise ledger of which relay protection devices you would need based on your configuration. So you'd get an engineer to kind of parse through that. And ultimately, like all stages in the project, getting intelligent generation's blessing that whatever you're doing for that other party's requirement won't somehow invalidate their needs. When it comes to a recloser and its functionalities, it's pretty typical for these large BESS projects, and a lot of those reporting mechanisms are pretty standard, would be a good way to say it. But you would obviously need to make sure that you're not putting control schemes in that would stop the battery from importing or exporting correctly. You couldn't use the recloser as a non-export system would be the most absolute version of that, because the battery's operations include exporting, right? So something like that would create an incongruence where intelligent generation's operating methods won't necessarily work. So that's what's really most important. At the end of the day, distribution automation is to protect you more than it's to protect the grid. And that comes, after a megawatt, your exposure to grid level problems goes way up. And then that's part of the thing too, is that if you're going to put in that system, ComEd requires you to protect yourself and therefore protect them from you. So I would say it's pretty typical, but make sure you get intelligent generation's blessing and make sure that you're not accidentally signing yourself up for export limitations.
Thank you.
I can add a little bit of context too, that I think responds to a couple of these questions. In that, I've been with the company for almost a year now, so I don't have a tremendous amount of experience. But since I've been here, I've been involved in quite a few meetings, discussions with our power partners about the interconnection process. So, we're available as a supporting role. We don't replace engineers, obviously, but we've seen a lot of interconnections be approved. We've seen a lot of interconnection applications come back with questions. We've seen a few get outright denied, which that's the first time I've seen that just happen a couple months ago. So, feel free to reach out to us. Feel free to ask us for, our thoughts or what we've experienced before, and we can be a good resource for you to support you in that process.
Thanks, Eric. And that looks like all the time that we have for today's questions. So if you didn't get a chance to ask your question, or maybe you just didn't want to, you can definitely follow up with our team and via email, and we'll get back to you. Nate, thank you so much for joining us and sharing F.utility's expertise on cracking the code with the utility interconnection. And Eric, as always, thank you for walking us through IG's post-close operational roadmap. For all of our power partners on the call, successful execution starts before construction begins. If you have active deals near closing, please reach out to your IG representative to review our post-close intake requirements and get your setup agree finalized so we can start the PJM registration clock as early as possible. As a final reminder, if you would like a copy of today's video recording, the slide deck, or the session notes, please shoot me an email and I'll get them over to you. Thank you guys again for joining us, and thank you for joining the Beyond Backup webinar series, and have a great rest of your Thursday, and we'll see you next month.
Thank you so much for having me, Khalif.
You got it.
See you, Nate. See you, Cleve. See you, everybody.
Thank you all.